for joining today to attend the presentation of our paper, RoomE and WatchBLoc, a BLE and smartwatch IMU algorithm and dataset for room-level localization in privacy-preserving environments. I am Alevizaki, and this is joint work with Professor Niki Trigoni in the Cyber-Physical Systems Group in the Department of Computer Science, University of Oxford. In this talk, I will first discuss the necessity of privacy-preserving localization in indoor spaces and introduce our proposed approach to addressing this very interesting task. I will then introduce WatchBLoc, a dataset that we collected and released in this work that is fit for this purpose, and then discuss the algorithmic details and performance analysis of our proposed method, RoomE. Finally, I will discuss some limitations of the current work and how this could be addressed in the future. Starting with the motivation for our work, in modern societies people spend a significant amount of their day at home. The COVID-19 pandemic forced the population of the planet to remain at home and redefined working schemes, allowing businesses to explore more flexible productivity schemes even in the post-COVID era. In the era of smart homes, this provides a unique opportunity to investigate how people interact with smart devices around the house. Besides that, however, we are also living in the era of aging population. Older adults normally have many more years to live with the help of the advances in medicine, but are often faced with age-related diseases that might keep them at home as they become more severe. In such cases, remote monitoring of older adults at home is essential to ensure their autonomy and also their safety, calling for remote intervention when required, for instance, if a fall occurs. In these scenarios, the people inhabit their living spaces while working, relaxing, preparing meals and doing other activities, depending on the place and time of the day. It thus becomes evident that human-environment interactions at home are tightly coupled with a person's location and mobility patterns around the house. As such, knowing where a person is during the day could significantly improve situation awareness in cyber-physical systems. In this work, we will investigate the indoor localization problem at home to ensure privacy-preserving, seamless location information for scenarios such as the above. A lot of work has been done in indoor localization the last few years. The advances in deep learning and computer vision allow for a variety of camera options. There are very accurate infrared positioning systems such as the Vicon system. Pedestrian dead reckoning has advanced significantly with the improvement of MEMS sensors. There are also passive RF localization options without the need for the user to carry any sensors, as well as a variety of indoor localization methods based on fingerprinting, crowdsourcing or map matching primarily, that have been developed for indoor spaces equipped with a large number of access points, such as hospitals or shopping centers. Most recently, smartphone-based approaches have become increasingly popular, most commonly fusing radio frequency signals, Wi-Fi or Bluetooth, with inertial sensors such as accelerometer, gyroscope and magnetometer. So is there already a solution to our problem? Not quite. The home environment has increased privacy constraints compared to public indoor spaces, which rule out constant camera recording. Some options are also cost-prohibitive, as installation and maintenance is cumbersome and expensive. Passive RF localization would be a great privacy-preserving option, but there may be more people using the space than the one in need of monitoring, thus making it impossible to identify the target person's mobility accurately. The number of available access points at home is also limited, and access to floor plans of the house, which are often used in conjunction with multiple access points in larger spaces, may not always be allowed to preserve the user's privacy. Finally, smartphones are becoming increasing in use, but it may not be practical to carry them around the house all the time. The phone may simply lie on a surface nearby while the user goes ahead with their everyday activities, inhibiting continuous monitoring. In this work, we propose a method to seamless, privacy-preserving localization at home. We assume a house with IoT devices installed around the various rooms, for instance, a smart TV in the living room, a smart fridge in the kitchen, etc. Given its ever-increasing popularity in the last few years, we also assume the user is equipped with a simple smartwatch that they regularly wear. The smartwatch is capable of sensing the ambient IoT devices from its vicinity as the user moves around the house performing their everyday activities. This is in short our proposed approach, RoomE, and we consider it to be a practical, infrastructure-free approach. To develop and evaluate our model, we also collected the WatchBLoc dataset. Our collected dataset is available on the Zenodo platform, an open-access, citable platform for disseminating research data and artifacts. WatchBLoc comprises of data collected by 11 users across 2 environments, yielding a total of 20 recordings, each supporting 3 IoT device configurations. All recordings are annotated with ground truth location information collected in real time by the user during data collection. We demonstrate here the floor plans of the two environments involved in the data collection experiment: a demo home, an office space adapted for the experiments, and a real home. Note the intricacies of the real home. It has a bedroom, a bathroom, an open-plan kitchen and living room space, and an ensuite study and loo space. This is an interesting environment to examine, as depending on the application, we might be interested in different layouts. The open-plan space may be accounted as a single location sometimes, or rather as two distinct ones, kitchen and living room, at other times. Similarly, the study and loo may each be a separate room or a single ensuite room. We will now introduce our proposed RoomE algorithm. The overall architecture works as follows. The user wears a smartwatch as they perform their everyday activities. The smartwatch senses ambient IoT devices from the user's environment and also records information about the user's movements in its inertial measurement unit. Each type of smartwatch recordings is first processed independently. The room detection module analyzes the IoT signals to infer initial location estimates, while the motion detection module provides mobility estimates using the watch's IMU signals. The two estimates are then fused in the room estimation module to provide a final informed decision on the user's location and over time learn a semantic map of the house representing room connectivity that can further ease the person's monitoring in the future. In the next few slides, we will discuss each of the three modules independently and evaluate their performance. Starting with the room detection module, we aim to obtain an initial location estimate for the user based on the devices sensed in their vicinity. In this work, we simulate ambient IoT devices with identical Bluetooth Low Energy beacons. We assume exactly one beacon to be present in each room of the house. After an initial preprocessing of the Bluetooth recordings to account for missing or surplus data, we obtain the BLE input to the room detection module. This is in the form of a vector of RSSI values for each time window, one value coming from each room around the house, and we assume n rooms to be present in the house. To obtain the location estimate, we employ a max RSSI approach. This means that we assume presence in a room to correlate with proximity to the beacon that is installed in that room. This is in agreement with standard log linear path loss models and is calibration-free, as it does not require any prior training on each user. Given this approach, the room detection outputs either the room from which the maximum RSSI value is received at each time, or the label unknown room where no RSSI value was registered in the current window. Let us first investigate how accurate the location estimates obtained with max RSSI are. First, in the demo home, then in the real home. One thing to notice is that the placement of BLE devices seems to be significantly affecting the localization accuracy. We are only considering two environments and thus cannot be conclusive, but it seems that there is no global configuration that can optimally solve our problem. The center placement is the best performing in the demo home, while the far one is the optimal in the real home. Second, the performance of users is highly variable within the same environment, and as can be seen in the real home performance, also highly variable for different layouts within the same environment. Recordings 13 and 14 account for 6 semantic locations in the real home. Recordings 15 to 18 account for 5 semantic locations, considering the open plan and ensuite cases respectively, while recordings 19 and 20 consider both the open plan and ensuite cases simultaneously, accounting for 4 semantic locations. The performance varies a lot across the 4 scenarios. It is also interesting to investigate in more detail some of the more lower performing recordings. This is a visualization of the ground truth versus the estimated location for recording ID 19 for the central configuration, which is particularly low performing. As can be seen, the ensuite and bedroom location estimates are highly confused, and there are a lot of missing data when the user is in the open plan and kitchen living room space. We will revisit this result again a bit later to examine the differences in performance in further stages of our method. So with this step, we have obtained an initial estimate of the user's room level location, but it seems it's not enough to accurately and continuously estimate the location of the user around the house. Can smartwatch IMU recording help us get more refined location estimates? Would it be useful to know when the user is highly mobile or when they are idle? Again, we first need to pre-process the data before we can use them effectively. To obtain our motion detection estimates, we employ an energy peaks approach. In other words, we want to estimate those points in time where the user's energy content is high that could be indicative of movement and thus potential room transitions. This is again a calibration-free approach. To realize energy peaks, we need to first further filter the preprocessed IMU data to the human walking frequencies, as we are only concerned about room transitions, which can be very well represented by walking events. The energy of the signal can then be calculated using the short-time Fourier transform. The final decision on the user's action is taken in comparison with the overall energy content of the user. As such, if the energy in a window is higher than the average energy of the user is considered active. Alternatively, they are considered idle. We evaluate energy peaks based on its ability to correlate real room transitions with estimated active events. Out of 555 real room transitions occurring in the WatchBLoc dataset, energy peaks effectively identifies 507 as active events, yielding an accuracy of 91.35%. Similarly, 97.04% of room stay events are classified as idle. The false positives for active may be high, but they actually only account for a very small percentage of room stay misclassifications, which could very well be explained by the user moving within a room, for instance, walking up and down while talking on the phone. We thus consider the energy peaks approach a very good estimate for candidate room changes. We will see how this can help refine the room detection estimates in the room estimation module next. To combine the two modules, we will use an appropriately defined hidden Markov model. As HMMs are a well-established mathematical model, we will not discuss their algorithmic details. We will only examine how they need to be adapted to work in our scenario. So, we define a hidden Markov model with the goal to infer the state of the model given our observations and our belief of the world, meaning the room emission probabilities, motion emission probabilities, state transition probabilities, and initial state probabilities. We define the state space of the HMM using one-hot encoding over all the possible n-squared room transitions. This means that each state represents a room transition from room I to room J. The observation space is then the tuple of the two initial estimates we obtained from the modules we examined earlier, and we assume these to be independent. Let us now initialize each of the parameters of the HMM. For the room emission matrix, we make the assumptions that once we are in a room, we are nearest to the BLE beacon that lives in that room. As such, we expect the largest RSSI value to arrive from that beacon. The probability of hearing that beacon from within the room it is installed will thus be high, and the probabilities of hearing any other beacon will be much smaller and uniformly distributed. Regarding the motion emission matrix, we need to take into account that people may move within a room without changing their semantic location, but it is impossible to move from one room to another while remaining idle. So we also define these probabilities accordingly. Next, we define the initial state vector by allowing the user to be in any stay within the same room state with uniform probability. Regarding the state transition matrix, recall that our state space is defined over room transitions. As such, state transitions should only be allowed between states that agree in their room transitions. The first part of the next state must agree with the final part of the current state. All such states have equal probability. Having defined all the components of our model, we are now in a position to examine how it operates to effectively infer the user's location. We will begin by first investigating the model's inference capabilities. If the model's parameters are carefully chosen, which we have done in the past few slides, the HMM should be able to provide relatively accurate location estimates already. Using the Viterbi algorithm for HMM, we can infer the most likely sequence of underlying states of the HMM for our room and motion estimates, which are the observations of the HMM. Given the room transition nature of the HMM states, we need then to decode the sequence of states to a sequence of most likely rooms. We can do that by giving the landing room from each state in the Viterbi path. We call this mode of function as room inference, as there is no need to refine any of the model's parameters based on the observations. We simply infer the user's location based on our assumptions of the world. In the second mode, we will refine the model's parameters using the Baumwelz algorithm, so that they better describe our observations. We need to do this only once per user, using a few hours of data, for instance, the recordings of one day. What is interesting in our scenario is that we do not really need to learn the full set of parameters. The reason is, we only need to use the motion estimates to refine the initial location estimates. As such, the model should always expect a motion event when in change room states, but not when in stay within the same room states. Similarly, when faced with unknown room location estimates, the model needs to work its way by only trusting the motion estimates. The unknown room observation should thus always retain a low probability of occurrence. This means that we only really need to learn the labeled room emissions and the state transitions. As these two types of observation, location and motion, are independent, we can simply multiply them to one emission probability in the Baum-Welch formulas. After learning the model's optimal parameters, we can use the Viterbi algorithm to obtain a refined location estimate, similarly as we did in Mode 1. Finally, we need to ensure that the model can not only report the user's location on historical data, as Viterbi normally does, but also in real time. To achieve this, we allow a memory of the most recent 12 observations, in other words, the observations of approximately the last 1 minute. We then calculate the Viterbi path with the available observations only, and report on the user's current location as the most recent state of the estimated Viterbi path. So now it is time to see how well we are performing. In these box plots, we summarize the performance of the original max RSSI estimates and then compare with the 3 modes of operation of our proposed approach. As can be seen, the performance improves from 67.77% in max RSSI to 80.46% in room inference to an even better 81.53% with RoomE. It also maintains a 77.60% accuracy in RoomE in real time. Let us also revisit the recording 19 that we examined earlier. The untrained model in room inference mode can effectively deal with missing location observations, but is not capable of significantly improving the confusion between the adjacent bedroom and ensuite spaces. However, this is effectively bypassed with RoomE, which accurately deals with disturbances due to the BLE RSSI signals, not strictly adhering to the max RSSI assumption. As a last step, we investigate whether it is possible to exploit the learned model further in order to obtain house layout estimates in the form of a semantic map. To achieve this, we will use the learned state transition matrix. First, we transform it to a room transition matrix. Then we remove the learned effect of the user's mobility pattern by normalizing the generated room transition matrix appropriately. The resulting adjacency matrix is our semantic map estimate. Comparing the ground truth adjacency matrix of the two environments with the estimated adjacency matrices, we obtain an impressive 97.58% similarity. We can examine an example of original and estimated maps here for the demo home environment. So, in this work, we have presented RoomE, a simple yet effective and robust algorithm for indoor localization, along with WatchBLoc, to our knowledge, the first comprehensive dataset to combine BLE signals and user-worn smartwatches under a variety of conditions: users, IoT device layouts, and home layouts. Still, there are a few limitations in our current approach that we hope to address in our future work. Unfortunately, we do not yet live in fully smart homes. As such, the assumption of an IoT device existing in every room of the house is not totally realistic for the time being. Could we still estimate the user's location effectively both for rooms that are equipped with an IoT device but also for adjacent rooms that are not? Next, as we have seen already through our investigation of recording ID 19, max RSSI may not always be the most accurate option. Even though it seems it can be well refined with appropriate mobility estimates, is there a more robust alternative that can preserve the simplicity and no calibration requirements achieved by max RSSI? A further interesting point comes from the fact that we do not only move between rooms when at home. In reality, we perform a variety of complex activities such as working, washing, cooking, doing chores, in addition or even sometimes in parallel to walking between rooms. Could our method benefit more from a more detailed activity estimate compared to the current simple mobility estimate to achieve a better location estimate for the user? We hope to address all these interesting questions in our future work. Thank you very much for your time. Happy to take any questions on Zoom.